Just a reminder that today we're going to talk about just one more example of expanding and condensing. Then we're going to work on solving logarithmic equations. A reminder of the three properties we discussed last week. There is the product property, and you don't need to know the names of the properties, you just need to know how to use them. And the first one says if you have a logarithm of two numbers being multiplied, you can write it as two separate logarithms being added together. The second property says if you have a single logarithm with two numbers being divided, you can write it as two separate logarithms being subtracted. And then finally, the third one says if you have an exponent inside of a logarithm, you can move that exponent out in front and multiply it by the logarithm. So those are the three properties we talked about last week. All three of those are going to be very important for when we're solving. Not necessarily for the expanding side of things, but for condensing. It's going to be a lot easier to solve an equation if we condense it to a simpler logarithm to deal with. And that's what we're going to look at first today. But we need to know how to expand as well, because it's good to know how to go both directions with that. So we've done a lot of practice with expanding and condensing now. This is just like the final review for it. Like these are the toughest the problems get, kind of. When we're expanding a logarithm, first we have to recognize how many numbers there are. So like in this example, there's 3 different numbers. There's the 5, there's the x cubed, and there's the y. And now I can go ahead and expand my logarithm and write it as 3 separate ones. Log base 6 of 5 plus log base 6 of x cubed. Let's do this differently. Plus log base 6 of x cubed minus, because the y was on the bottom, log base 6 of y. And whenever we're expanding, we want to do that first. Some people see the exponent, the 3 here, and want to drop that out in front. But what that would do is that would have 3 times log base 6 of 5, which is not true. 5 is not being raised to the third power. Y is not being raised to the third power. So we want to wait and do that part second. So once I have it rewritten like this, now I can go ahead and drop that 3 out in front, and I get log base 6 of 5 plus 3 times log base 6 of x minus log base 6 of y. And that's how I would expand this logarithm completely. All right, get rid of all the exponents, and you just want one number or one variable by itself after the logarithm. That's how you know you're fully expanded. Okay. So we've done that a few times on the last couple assignments, including assignment 15 that's due tonight at 11:59 p.m. That has some expanding practice. That assignment also has some condensing practice, and this is also very important for when we want to solve logarithmic equations. So the condensing one, I want to put these equations back together. And with condensing, the very first thing I want to deal with actually is any exponents. I want to put those back in first. So for example, this is log base 10 because there's no base written down. But there's a 3 there. I want to put that 3 up and write that as 2 to the third power. So it'll be log base 10 of 9 plus log base 10 of 2 to the third minus log base 10 of 3. And now, because I'm dealing with numbers and not variables, I can rewrite 2 to the third as 8. So that's what 2 to the third power is. And then I can just work from left to right, condensing these logarithms. Log of 9 plus log of 8 can be rewritten as a single logarithm, 9 times 8. 9 times 8 is 72. So I get log of 72 minus log of 3. And then, because I have 2 logarithms being subtracted, I can write that as division inside of a single logarithm. Log base 10 of 72 divided by 3. And 72 does go into 3 cleanly, so I get log of 24 as my final result there. And this is why condensing is so important, because if I did this correctly, I just turned 3 logarithms into 1 logarithm, and it's log of base 10 of 24 now. That's a heck of a lot easier to deal with than 3 separate logarithms that I would have to work with before. So that's why condensing is so important, especially when we get to solving logarithmic equations, which is what we're going to be practicing today. Now, your chance to try. I have 2 practice problems here, one expanding, one condensing. I'm going to give you guys a couple minutes to work on those now. If you have any questions at all, please let me know and I'll answer those in the chat. I went ahead and wrote down the answers for 1 and 2 for you, so you can check your answers on those too. But again, for problem 2 specifically, we see that it was 3 separate logarithms and we condensed it to one single logarithm. It should come out to natural log of 40 after we're said and done. And that's just because we first wrote the first one as natural log of 4 to the 3rd power, which can become 64. And then we just work from left to right. We say 64 divided by 8, and that gives us 8. And then we have natural log of 8 plus natural log of 5, and then we can do 8 times 5, and we get natural log of 40.
So how do you decide like which ones to combine? Because my mistake was to add the 8 and the 5 together and then get that out to natural log of 35.
Got it. So yeah, the problem with that is if we were to write this all back together as one thing, since the 5 is being added, that's a multiplication situation. So if we wrote this back together as one thing, it'd be natural log of 4/3 times 5 over 8. So the 5 is not in the denominator of the fraction, so that's what you have to be careful of. That's why I'd recommend working from the left to the right.
Well, I did. I put natural log of 4 cubed minus natural log of 35 because I multiplied the 8 and the 5 together.
Yeah. 8 times 5 is 40, but
oh, okay. Well,
but then yeah, what happens is the 5 can't be multiplied to this 8 because this 8's in the denominator of the fraction. It's because it's a negative one. That's what's really weird. That's why you should work from left to right when you're working on these particular problems. If there were parentheses here, then I'd want you to do the 8 and the 5 first, because then what happens is you could do the 8 and the 5 and that would all be in the denominator, and then you would say that's a negative natural log of 8 and a negative natural log of 5. Does that make a little bit more sense? But only if there are parentheses there. Otherwise, you got to work from the left side to the right. So good question there to clarify how you want to solve these types of problems. Okay, any other questions on these expanding condensing types of problems? Okay, so then we're going to look at solving logarithmic equations next. The first thing I want to talk about algebraically is called the property of equality for logarithmic equations. It sounds scary, but it's actually pretty cool and pretty easy. It says if b, x, and y are positive numbers where b does not equal 1, then log base b of x equals log base b of y if and only if x equals y. It's basically saying if I have the exact same logarithm with the same base on both sides of the equation, and that's all there is, then I can get rid of the logarithms and just say x equals y. A good example of this is log base 2 of x equals log base 2 of 7. That means x has to equal 7 for those equations to be balanced. Similarly, if x equals 7, then log base 2 of x has to equal log base 2 of 7. So the best way to actually show you this is this first example here, which says solve log base 5 of 4x minus 7 equals log base 5 of x plus 5. We have 2 logarithms. There's nothing else being added or subtracted. It's just the logarithms on each side. Then what we want to do is we can say, okay, well that means that 4x minus 7 has to equal x plus 5. So we take what potentially looks like a scary equation and we make it something that's much more simple to solve. Because now we're saying, well, 4x minus 7 has to equal x plus 5. Subtract x from both sides, you get 3x minus 7 equals 5. Add 7 to both sides, you get 3x equals 12. Divide both sides by 3, you get x equals 4. And that's how we'd solve for x algebraically here. Of course, we want to do a check. Always want to check. And what you'll see is when we check it, 4 times 4 minus 7 equals log base 5 of 4 plus 5. And we'll see that the right side is 9. So we're hoping that the left side also equals 9. Log base 5 of 16 minus 7. 16 minus 7 is indeed 9. And that's how we know we did it correctly, because you get log base 5 of 9 equals log base 5 of 9. That's a true statement. So we know that x equals 4 is the correct answer there. All right. That's how the property of equality for logarithmic equations works. As long as you have logs on both sides and there's no other numbers being added or subtracted, that's all you need to do there. Okay. So something else here is that we're going to start talking about is what's called extraneous solutions. Have you guys heard that expression before, extraneous solutions? Did we talk about it last year in AGS2, or we talked about? I don't think we've talked about it this year at all. Okay, so an extraneous solution is a solution we find algebraically but it's outside the domain of the function. So it's something where it's like you find it and it should work, but then it turns out that if we set the domain of the function, it's outside of that domain. That's what an extraneous solution is. A good example, or just a quick example, I'm just going to make up some numbers here. But if we have a parent function like y equals log base 2 of x, we know the domain of that parent function is going to be 0 to infinity. So that's the domain of the function, 0 to infinity. The range of any function is negative infinity to positive infinity. So what we do then is we have, if we had two possible answers, like let's say we solved some equation for this and we got x equals 4 or x equals negative 2, then one of these would be an extraneous solution if we solved algebraically. I just made these numbers up again. These are not real answers. I'm just saying if we did find some answers for this. And we got x equals negative 2, that would be our extraneous solution because negative 2 is outside that domain of 0 to positive infinity. So we would just cross it out and write down the word extraneous like this. That's how we'd want to represent an extraneous solution. Basically, it's just a solution that we find algebraically, but it's outside the domain of the function. This first example, we found the solution algebraically, we checked it, and it worked, so it's definitely inside the domain of the function as well. So that's good news for the first example. We're going to do one where we check an extraneous solution here in a second too, and find one. Okay, so are there any questions right now on extraneous solutions, or we can just wait till I show you one in just a second here? Okay, let's take a look at the second example. It says log base 4 of 5x minus 1 equals 3. So this time we can't just use that property of equality for logarithms because there's only log on one side. So what we can do is we can change forms. That's one possibility we can do. I'll zoom in here. Say change forms. And what that means is the base of the logarithm becomes the base of the exponent. Logarithms solve for exponents, so the exponent was 3. And we'd be left with 5x minus 1 on the other side of the equation. Now the change forms thing has been something we've been doing like since the beginning of the module when I first introduced logarithms to you. And if you don't like the change forms, if you prefer an algebraic method, then let's talk about that too, because personally, I do better with algebra than I do with like changing forms and memorizing this weird thing. But I'm really good at keeping equations balanced on both sides. So that makes much more sense to me, personally. So let's take a look at this. The other way we could do this, we have the equation was log base 4 of 5x minus 1 equals 3. What we could do is we could do like base 4 of both sides. And what that means is we put a base 4 and we raise everything to an exponent. Like this. And it looks pretty scary, but it's not too bad. It's 4 to the log base 4. I chose base 4 because the logarithm already had a base 4. That's why I wanted to do base 4 here on both sides. And what happens is the 5x minus 1, it's just like properties of logarithms where that's allowed to move out front and be multiplied by the numbers. And then you're left with 4 to the log base 4 power. And that's essentially a 1. Just like what we did before, if you got log base 4 of 4, that would be a 1. That's the same thing the other way. So we'd end up with a 5x minus 1 equals 4 to the third. And we got to the same step we did as if we changed forms. But we did it with an algebraic method of balancing, keeping the equation balanced. I didn't need to memorize where to move all the numbers to. So if you like that more, where you do a base 4 of both sides, you're more than welcome to do that. It's entirely up to you though, whatever you're comfortable with. All right? It does not matter how you do it. If you like to change forms like this, that's fine. But now from here, we should be able to solve the problem. 4 to the third is 64. Start by adding 1 to both sides. We get 65 equals 5 to the x. To get x by itself, we're going to divide both sides by 5. And we get x equals 13. And that should be our solution. We want to double check. So we'll do our check over here. Go back to the original equation. Log base 4 of 5 times 13 minus 1 equals 3. And when you're running your check, you should see a lot of familiar numbers here. For example, 5 times 13 is 65. Hey, look, 65, 65. 65 minus 1 is 64, and we had a 64 on the other part of the equation already too. So it's like, because it's working backwards through the steps, so we saw the 64 already. And then if we did log base 4 of 64, you could either put that in your calculator or you can change forms to use the change of base formula to put that in your calculator. And you should end up getting like a 3 equals 3. And that verifies the left side of the equation equals the right side of the equation. So x equals 13 is a solution, and it's in our domain, so it's not an extraneous solution. Okay, that's our second example, second type of problem we might deal with on the assignment tonight. Last example here. This one is the toughest one by far. It's got 2 logarithms. They're both base 10, but they're both on one side of the equation. So this is where the condensing comes in handy. It's going to be a lot easier to deal with a single logarithm than it's going to be dealing with 2 separate logarithms. And because I have 2 logarithms that are being added together, I can write that as 1 logarithm being multiplied. So I write log of 2x times x minus 5. And then I'm going to distribute the 2x there and just multiply everything else out inside. 2x squared minus 10x. And then from this point, It's base 10, so I could either change forms or I can say, let's do base 10 of both sides. Because I do base 10 of both sides, it's keeping the equation balanced. And then the 2x squared minus 10x moves out front. And then I basically have 10 to log base 10, which is just going to go away. And I'm left with 2x squared minus 10x equals 10 squared, which is what I would have gotten if I had just changed forms. But if I don't want to memorize that change forms thing, I can do this instead. Use an algebraic method. Now, this is where some old school AGS2 skills are going to come in, because we're back to a quadratic equation here. 2x squared minus 10x equals 100. In order to solve a quadratic equation, first thing I'm going to do is I'm going to subtract 100 from both sides. 2x squared minus 10x minus 100 equals 0. Whenever you want to solve a quadratic equation, you have to get the quadratic function on one side and a 0 on the other. Next, I see all of these are factorable by 2, so I can divide a 2 out, and that's going to make this quadratic equation a little easier to work with. 2 divided by 2 is 1, so I get 1x squared. 10 divided by 2 is 5, and 100 divided by 2 is 50. 0 divided by 2 is 0, which is why I'm allowed to do that. Just get rid of all the 2's. I'm left with x squared minus 50, or minus 5x minus 50. Then I need to work on factoring this. I could do quadratic formula. I can complete the square. I can do a factor method. The factor method that I would use if I was teaching AGS2, and some of your teachers probably used last year, is the box method. Depends on which teacher you had last year, might have used this one. But then you have to ask yourself, what are the factors of 50 that they're going to, since it's a negative 50, one has to be negative, one has to be positive, and they have to have a difference of 5, the two factors. So for example, factors of 50, 1 and 50, but their difference is 49. 25 and 2, but their difference is 23. 3 does not go into 50, so that's not going to work. 4 goes into 50, it does not go into 50. 5 goes into 50 10 times, and their difference is 5. So 5 and 10 would work. So I could say minus 10 there, plus 5. I want the bigger number to be a negative, because I want a negative in the middle, and that sure enough works. So it turns out x minus 10 and x plus 5 are my two factors here. So I just rewrote this standard form quadratic into factored form. Something else you could always do is you can always graph it and look for the x-intercepts and then write those factors out. So if that helps you, some sneaky ways to get through quadratics here. But unfortunately, even dealing with logarithms, we have some quadratic equations sometimes. Now I can use the zero product property, which says that one of these numbers has to be equal to 0 if you have two products that are multiplied together equaling 0. And we end up getting two results for x. We get x equals 10 or x equals negative 5. Those are our two possible results. Then we'll go ahead and check our answers. All right, first one I'll check is negative 5. We'll do log 2 times negative 5 plus log of negative 5 minus 5 more. And then this becomes log of negative 10 plus log of negative 10 equals 2. And right there, I see a problem. I have negative 10s in my logarithms, and if you try and take a log of a negative number, it's not going to work. So what I mean by that is, like, let's actually try it. I'll do negative 10. I'm just going to do it on my phone here. Turn my calculator sideways. I got negative 10 in there, and I hit the log button, and it'll just say error. It's impossible to take a log of a negative number. So that means that -5 is actually outside of my domain. So that is, even though we found it algebraically, turns out that is an extraneous solution. That's what they look like, is when we're checking it, we end up getting a negative value. Because what's really weird here is I can check it and it's still going to work. It's still going to get me 2 = 2. Because the next step, I would take -10 times -10. What's a negative times a negative? A positive. And I get log of 100 = 2. And then if I do log of 100 in my calculator, I would get 2. I'd get 2 = 2. So it looks like it's going to work, but right here is the key. Those -10s inside the logarithm, because if I were just to take a log of a -10, it's not going to work. I'll show you what this looks like graphically as well. Now let's check the other one. The other one I used +10. And I get log of 20 plus log of 5 = 2. That becomes log of 20 times 5 when you condense this to a single logarithm. And 20 times 5 is 100. Log of 100, we already said, is 2. We get 2 = 2. So this one works. So it turns out we found 2 possible solutions. One of them turned out to be extraneous. One of them did work. Sometimes both of your solutions will work. Sometimes neither of them will work. So it's always important to double check. And you can check it a few different ways. One, you can do this algebraic check and look for negative numbers inside of a logarithm. That's a good sign right there that you're going to have an extraneous solution. And the other way you'll check. So again, these are the 4 possible solutions. And if you find an extraneous solution, make sure you write down extraneous for that one. Just cross it out and put the word extraneous across next to it. So that way I know that you know how to find it algebraically. That's really important that you do that. Okay. So you write down, hey, there's 2 possible solutions. Turns out only one of them is a real solution. For number 3, that was x = 5. For number 4, that was x = 4. Typically, when we're looking for extraneous solutions, it's usually a negative number because most logarithms are going to be opening to the positive side. But you do need to double check because sometimes a logarithm can be shifted super far into negative territory. So you always want to double check to see if they're extraneous or not. All right, so that's really important that you do that. Any questions on these 4 before we move on to the last topic of the day? Okay, so last thing to talk about today, solving exponential and logarithmic equations by graphing. So in this class, I am going to require you to show your work so I can see your algebraic work, your algebraic methods. But on like an SAT or an ACT, which is a multiple choice test, it's really useful to go through these questions quickly by using a graphing calculator, which is legal on a test. So make sure you can do that. What you'd want to do is you'd want to start by writing each side of the equation as y. Each side of the equation as y equals. So for example, y equals log of 2x plus log of x minus 5, and y equals 2. And on this right side, you just write it as y equals log base 5 of 5x minus 1. And then the other one would be y equals log base 8 of 3x. So you'd want to write something like that. Then you want to look for the intersection of the 2 lines. Because it's a multiple choice test, that's perfectly fine on an ACT or an SAT just to graph them and then identify the intersection, and that should be your solution for these particular problems. Okay, so that's a great great shortcut for a test like an SAT or an ACT where the time is so valuable and you want to get through as many questions as possible. I'll show you this real quick on Desmos too, what I mean by look for the intersection.